For our zero order reaction, this should look very similar to what we drew on the last slide. But you'll notice with first order, we actually see the rate slowing down, or the concentration changing less, okay? And the second order is even more drastic. So these plots can be harder to, the first and second at least, can be harder to get data from simply because they're not linear. So that's why we don't plot everything as concentration of A versus time. Okay, so let's do another exercise here. Let's draw a plot that represents a zero order reaction with some rate constant K. That's supposed to be some. That's an O. And then we're going to draw the linear plot. After you have one done, so you're just basically repeating what you did, then I want you to add another set of data, or another line for a reaction with a different starting concentration. Okay? So how's that going to change things? So we drew the last one. We all agreed. We have concentration of A versus time, slope of minus K. All right, but what happens if you have a different starting concentration? What's that look like? Take a couple seconds. Does anyone want to make a guess? Suggestion? Yeah. So she's saying that basically the only difference is going to be where it intersects the y-axis, and that's true. So we're saying that just the concentration, initial concentration, is changing. We know that's where we cross y, and the rate constant's not changing. So it should have the same slope, just starting at a different place. It could be higher, lower, wherever. Okay. But this is what two different concentrations would look like on your plot.
So that would be different, I guess, if you had two different solutions. Obviously, the slope would be different. The starting point would be different.
If you had two different solutions of the same thing. Different things.
So it would be a different slope.
Yeah. If you have two different reactions happening, the rate constants will most likely be different, and when the rate constants are different, those slopes are going to change, which is going to bring questions on that. As to the next problem. Thank you. So on this one, we've got our first order reaction. Again, draw your plot, and then draw a second set of data for a reaction with a different rate constant. Same starting concentration. All right, anyone want to suggest what this should look like? Yes?
They'll have the same y-intercept, but different slope, but slope less negative.
Yes, same y-intercept, different slope, but slope still negative. Sounds good. So you could draw it a number of different ways. Something may look like that. Okay. Make sense? So let's go back. Which one of these plots is going to have the larger value of K? Negative, it makes it harder. Yeah? Blue line, do we all agree? Rise over run. seems right. Okay. All right. Okay, let's just move on. Actually, okay, so another important way of determining or looking at these types of reactions and sort of arriving at quick answers is to be able to do unit analysis, or at least recognize the units that are associated with the order of the reaction. I'm not going to go through every one of these and do the unit analysis, but essentially what we're going to come up with is what the units should be for first order, what they should be for second order, and what they should be for zero order. And when you see those units, you should know what the order is for the reaction, because they're not going to change in any way. So you guys know how I like to do my unit analysis. So what I'm going to do is plug in my units for first order reaction. The first thing I've done is set, sorry, I got ahead of myself here. I've set the equation equal to the rate constant K. And now I'm going to substitute in the units. So we'll have moles per liter for our units for concentration, and we'll use seconds for our units for time. Now, time doesn't have to be in seconds. This is one of the most common units you'll see, at least in this course. Okay, so we have natural log of moles per liter over moles per liter, all divided by seconds. And moles per liter are going to cancel with each other. We don't need to worry about our natural log. So the units on our rate constant for a first order reaction is going to be inverse seconds. Okay. You can go through and repeat these for second order and zero order. I've set these equations again equal to the rate constant. And so for a second order reaction, what you'll find is the units are going to be moles to the minus 1, moles per liter to the minus 1, seconds to the minus 1. And for zero order, it's going to be moles per liter times seconds to the minus 1, or moles per liter per second. Okay. Knowing to recognize these and what they are, that's going to be, yeah. Okay. So again, very useful for you. Okay, so another thing that we often, oh yes, question.
Can we infer order based on units?
Say that again.
Can we infer order based on
Yes.
units?
Yes, you can definitely infer order based on units for the integrated rate law. Now, when we were doing rate laws that weren't the integrated rate law, and we had rate equals K times reactant raised to some power times reactant raised to some power, those units are going to be, they could be crazy. They could be anything. So that's different. Okay, so half-life. Half-life is a very useful calculation. You'll see this come up when we're talking about nuclear chemistry, half-life for a radioactive isotope. You might see like LD50 values or something like this if you're looking at different drugs and how LD is like some sort of dosage, like when half the mice die or something terrible, I don't remember. But these are sort of all related to half-lives. Okay, so the half-life is defined as the time that's required for a reactant to reach half its original concentration. So we call the half-life special T1/2, but what we're really saying is that the concentration after some time is 1/2 the original concentration. Okay. And so what we can do is we can use this definition for half-life, plug that into each of our integrated rate law expressions, and solve for an equation for a half-life for first order, second order, and zero order reaction. So I've set that up here and actually gone through for the first order reaction. So we've got our first order expression, natural log of the concentration at some time t over the initial concentration equals minus k times t. So this is the equation before we made it into the equation for the line. And so then we take our definition for half-life, plug that in, and we'll have natural log of the original concentration of A divided by 2, because that's equal to A sub t, divided by the original concentration equals minus the rate constant times T1/2. So this T1/2 is just signifying half-life. When we divide out in the natural log, we get natural log of 1/2. And that's equal to minus the rate constant times T1/2. And taking natural log of 1/2, and then dividing by the rate constant, setting equal to T1/2, we get equals 0.693 divided by K. So this is really cool for the first order reaction. The half-life is not dependent on the initial concentration, okay? It's only dependent on the rate constant. So no matter what size pile of uranium I have, okay, nuclear fission is first order decay, the half-life is going to be the same, okay? That's not true for second order or zero order. I can't remember if your book goes through the derivation of these, probably not. But for the half-life for second order, it's 1 over K times the initial concentration of A. So it is dependent on the starting concentration. And for the zero order, I don't really like how these are showing up. So A0 over 2 times the rate constant. Okay. Questions on that? Yes?
I just click for the top one, the A0B and the B1, right?
I actually need to check. I don't want to do it wrong. I guess we could derive it if we really wanted to, or we can Google it. Yeah, that makes sense. Okay, so that's a little cleaner. Okay, other questions? Yes? Oh, good question. These are also on the exam. Forgive me. I am really working on getting that equation sheet posted and practice exams, so hopefully soon those will go up. In terms of prepping for the exam, it's probably best not to start with the practice exam anyways, so go through, make sure you're good on homework, make sure you're good on those recitation activities. When you get those practice exams, take them as if it's a real exam. That's my best advice. Set up a 70-minute time limit, no books, your calculator that you're allowed to have, and see how you do. and go back after that. But yeah, that's my best advice for that. Okay. Let's get back on track. All right, so here's one of those problems where I was saying plotting data can be useful to tell you a reaction's order. So we're given a reaction of dinitrogen pentoxide. The reaction was studied at different times, concentration was recorded at different times. It's given in the data table. And I think I took this from either your book or another book. But basically, it says to verify the reaction is first order. And so one way of doing that is plotting natural log of A sub t times t. And you should get a straight line plot. If you don't get a straight line plot, it's not first order. So the fact that it said verify it's first order means you only have to plot one thing, right? If it just said what order is this, then you get a little bit grumpier. But this one wasn't so bad. So on the next slide, I plotted it. Plotted natural log of the dinitrogen pentoxide concentration versus time. And I get a slope of minus 0.0069. Okay, so that's our rate constant, negative rate constant. Okay, questions on this? This is just plotting the data, fitting the data. Something you would do in Excel, where we calculate, probably not on your iPad because it's torturous. Okay. So the next thing we could do would be to calculate the dinitrogen pentoxide concentration at 150 seconds after the start of the reaction. We know it's first order. We just verified that. Before we even get started, we've got this data sitting here, so we can actually make an estimate for the concentration based on this data. So we're looking for the concentration at 150 seconds, which we know will lie somewhere between the 50 and 200 seconds, closer to the 200, okay? So we're hoping to get a concentration somewhere between these two values, the 0.07 and the 0.02. If we don't, we've done something wrong, okay? So that's our goal. And so essentially at this point, we sort of plug and chug, as they say. So natural log of A at some time t, that's what we're solving for, where our time is 150 seconds. We know our k value from the plot on the previous slide. It was minus k was minus 0.0069. And we're at 150 seconds. That's what we want to know. And what's our starting concentration? 0.1. Yeah, so at time 0 or at 0 seconds past, our concentration was 0.1 moles per liter. I dropped a 0. It's okay. And then in calculating this out, we'll end up with natural log of A at some time t is equal to minus 3.34. Okay. So make sure you know how to take the anti-log on your calculator. So we're going to do E. And you should end up with the concentration of A at some time t is equal to 0.0356 moles per liter, which falls where we expected it to fall in our data table, so that's good. Questions on yes?
Really quick, just where the 0.0069
Uh-huh. Where? Oh, that's from the previous slide. We did our rate constant from the plot. Other questions? Okay. The slope is minus k, and we have a negative here, so it cancels out. To derive another equation from this. Yes. Let me see. Yeah, that's what I'm thinking, right? You want for our first order reaction like we did previously. Next we can calculate the half-life of the reaction. Yes.
Sorry.
Yep.
Could you just plug it into the
You could. Yeah, because that's the same. It's gonna give you the same thing. Yeah. We hope. Right. Okay, so calculate the half-life. First order half-life calculations are super nice. You only need to know the rate constant. We know that from our previous slides. T1/2 equals 0.693 divided by 0.0069. And we get about 100 seconds. You can kind of estimate this as well from the data. Okay. Questions on that? Yeah.
You should assume as an absolute value from K.
So, but you should get a positive number for time. Any other questions? Okay. 3/4, will that give you too big of a number? 1/4. So, one more here. How much time is required for the reaction to be 75% complete? So, I'll let you think about that for a couple seconds. Come up with some ideas on how to do this. And then we'll regroup. All right, what'd you guys come up with? Yeah. Yes.
First of all, just looking at the table, you can see that the third data point is already 75% of the way done, so you know it's 30 seconds.
Yeah, so you know it's 75% of the way done. Okay. What if you didn't have this data table? This is the right answer though, but yeah.
Well, then you can say it takes 100 seconds to get the first 50% of the way done, and then to get the 25% that would be 100 more seconds.
Okay.
Or then get half-life of the second half of the reaction.
Yeah, so there's another way. You got 2 half-lives. So you could calculate that twice. What else?
You change the 1/2 as the multiplicative constant 3/4.
1/2 to 3/4. Another way of doing this, there's a bunch of ways. So you may not always get a nice round number, 25. You may not have the data table. So we know that 25% is left. So we know that A at time t is equal to 25% of our original concentration. So we want a quarter of our original concentration. So your calculation would be if there was, if it was 25% complete. And now you can use this, plug it back into the equation.